Welcome to our presentation about SP2 carbon and seafoam. SP2 Carbon is a company that focuses on antistatic performance, EMI shielding, electrical static performance, and what we do basically is we bring conductiveness to the composite industry.
Hello, I'm Rudy Olson. I'm the GM and CTO of Seafoam, and we make carbon foam from coal in West Virginia. If you look at the state of West Virginia, it looks like this. You have to be very careful how you do this, but we're actually in the finger. Our carbon foam is utilized for composite tooling, also as a composite core material. It's a lightweight structural material, thermally stable. It's utilized for EMI shielding, very fire resistant and corrosion resistant.
The topic of our discussion today is about EMI shielding, thermal electrical conductivity, and how we bring it to the composite industry. What do we do? What do we use? It's graphene, it's 2D material, and it's a combination and applying of those technologies into the composite industry. We're going to go through some of the application, a little bit about the discussion. What is graphene? Where is it used? And what does it mean in terms of antistatic? And then Rudy will also explain a little bit about seafoam technology and how those two technologies in alignment are a very interesting novel technology for the composite industry. So how do we do this? Again, graphene overview a little bit. We're going to show you some of our results in terms of R&D. And we also focus on application so that you get a little bit of an idea, not only what's possible, where is it used. My name is Christian Oberleitner. I have been in the composite industry for about 30 years, between resin and glass, and also on the compounding side. So one of the most modern carbon SMC production lines, so some of my colleagues here, is actually placed in Hamburg. So there's a lot of experience between glass, resin, different reinforcements, and compounding. SP2 Carbon itself. We are a small, dynamic global team in Europe, in the US. We're based in LA and also in Asia. We are producing graphene, or used to produce graphene ourselves, but we have the whole supply chain from graphite to graphene. And the majority of our work is help our compounders, the customers, yourself, to make sure that the graphene performance and the properties that that novel material has is getting translated into the final parts. And that's why we're here at the JC. Now, why is it important? Why would we already do this? So we formulate and we actually take an insulating material, polyester, vinyl ester, epoxy, phenolic resin, and make it conductive. It's counterintuitive. Why do we do this? Because there's some application where if we try to replace metal, use weight-saving properties, there still might need to be shielding and electrical conductivity performance needed, and that's where metal is really, really strong. With SP2 carbon, with graphene, with that technology, we can add that missing link of technology to the composite industry. That's one way of a picture how graphene could look like. What you see here is basically one layer of graphene, which is graphite, which used to be, and about 12 years ago, this was identified as a single product by two Russians. They actually got the Nobel Prize for this. And they're still based out of Manchester. There's a big university, about 20,000 people, investigating how to produce graphene, how to bring it into different technologies, composite being one of it, but there are many others. And I'll show you a little bit of a screen. So what you see here, is basically a typical opportunity where graphene is used, and composite being a very little part and segment out of it. Now, graphene is very difficult to identify. What is graphene? At the end, it's a single layer of carbon. That single layer has attributes which are outstanding. That means it's 200 times stronger than steel. electrical, thermal conductive, flexible, and transparent. So basically anything we learned in the university, you can close that book and say, okay, this is impossible. Those priorities and properties don't match, but they do when it comes to 2D material. The single layer, which is the orange down there, is really the high end. That goes into battery, into storage, also very expensive and difficult to produce. The composite industry can benefit from that, but it's not necessary. So what we focus on is basically single multi-layer, meaning 5, 10, 20 layers of those graphene layers, or bulk. Bulk means there's a borderline going back into graphite. What we do with those technologies means that we bring in the graphene at the right particle size, in the right distribution, to allow for the electrons to flow through the system and are not stopped by the insulating epoxy or resin material, because that's the job it's supposed to be doing. Some of the application, a big one that the whole industry has been chasing, and obviously it's an interesting one because everybody knows about e-mobility. We can calculate how many batteries we're going to be produced, how many cars we want to put out. The battery basically has two fundamental problems. One, during the drive, you want to constantly recharge to extend the kilometers or mileage out of the car. And if there's a fire, it's still going to be a challenge to get out of the car and to secure safety and make sure that nobody gets hurt. Now, this is done with metal right now. There's different opportunities for composite to replace that metal parts, whether it's a hybrid between metal and composite or it's a pure composite. It's to be developed. But if you use composite, one thing is clear. It needs to be shielded, because you're sitting on that battery, basically, and during the recharging, it's an electromagnetic field that has to happen. And this is not good for human being. Other applications are basically medical devices where you still deal with the same situation. You want to protect the people being exposed, electromagnetic field, and to electrical discharge. Different ones, telecommunication, information systems, so anything that has to deal with different wavelengths. And then shielding is going to be the key. So what do we do? How do we get this into the system? You can take the graphene, mix it in, and you're going to be successful? Unfortunately not. That's part of the reason why it took about 3 years to really make sure that we get the graphene into our system that is compatible with the resin, with the cure, and most importantly, with the molding and the production of the parts. With this, I would like to hand it over to Rudy, because part of the discussion is seafoam technology, and then we will revert back to what the combination of both technologies could mean for the composite industry.
Thank you, Christian. Again, my name's Rudy Olson, GM and CTO of Seafoam. My background, more in ceramics, metals, and carbon. The last 20 years has largely been in foams with those materials. Some of the basics I want to get across, these pictures here, you can see are of our manufacturing facility. We can do approximately 3,000, we have 3,000 square meters of manufacturing space. We can do about 20,000 cubic feet of material a year. The picture on the right there is a close-up of our carbon foam. Our manufactured density range is in the range of about 0.3 to 0.6 grams per cc. So very lightweight, but also structural. A couple of the attributes of seafoam that are really attractive for some of the applications we talked about. One is that it has a very low coefficient of thermal expansion and a very high thermal stability. Carbon will oxidize at about 370 to 400 C, but it will do so very slowly. If there's not a whole lot of oxygen around, the seafoam, the carbon foam, It's not going to melt, and it will persist up to 2,500 degrees C or more. Very fire resistant. We're going to see a video of that in a second. Some of the materials here in this graph you can see, seafoam is the one in the middle with a CT of about 5 ppm per degree C. But then you see steels up around 13, aluminum 23, Ren board you're getting to 36, polyfoams are 47 or more. So very good for thermal shock resistance, also very good for composite tooling and making composite parts that have good reproducibility. The material is very inert, so it has both excellent acid and base resistance, so good for batteries. Also has excellent fire resistance. And the next slide, we're going to see a video of seafoam with a very thin piece of refractory coating, just to give you a demonstration of the performance of seafoam. So you can see this is a torch centered on the front face with that thin piece of refractory coating. If you put your hand on the back of this plate that's probably about 50 millimeters thick, you can touch it with your hand. So you're definitely, you're below about 50 degrees C. The other component with seafoam, the other property is it's very machinable. So you can see here a component being machined with a CNC with a small end mill. You can create very complex shapes. The one on the bottom right here is actually a tool for carbon foam winglet. The point I'm trying to make here, not only you can machine it into a complex shape, but you can also coat it with various materials. Carbon foam, matrix, epoxy, different types of polymers, and that's where we see a synergy with SP2 carbon. That's their specialty is making conductive coatings. And so I'm going to turn this back over to Christian, and he'll talk a little bit about the combination of our two materials.
Thank you, Rudy. So we called it intrinsically conductive polymers. So what does that mean? We'll take any resin chemistry, that's basically our background. We designed the chemistry to fit it with the graphene and the carbon. And it's a designed molecular weight of the resin that carries the graphene and the carbon content to an optimum level, allowing for the electrons to flow or for the thermal energy to be dissipated over a larger surface. Now, this additive comes in different variations. So we try to produce a concentrate as high as possible, allowing for our customers to use as little as possible. So you're not dealing with the powder. Nobody should be dealing with the graphene because it's a 2D material, very low density, difficult to handle. And that's, like I said, part of the problem in the industry, or the challenge, was that the graphene being added in many different versions, sometimes it worked, sometimes it didn't. And it's all about the optimal distribution and molecular weight together with the resin to make sure that system is working. So we're designing those additives. So we have concentration for different technologies, including phenolic. And part of the things that we have done, and I wanted to take the sample there, not the other one. We talked about battery. So one of the challenges SMC, BMC, pultrusion is trying to find a hybrid between metal and composite. Now, the sidewalls are difficult because you also have, if there's a battery on the floor of the car, you have an impact in terms of accidents. So the mechanical performance is almost as important as the shielding. Now think about the combination of a foam that is on the side of the battery box, plus an SMC produced or a continuous panel, even in phenolic or in polyester resin or vinyl ester, depends on the final criteria that we need to match. And you have a conductive, lightweight, high mechanical performance from the seafoam. you get conductiveness from the top layer for the shielding, and in case of fire, which is one of the biggest problems for the battery, that conductivity anticipates the temperature, which means it's going to raise the overall performance of the box and of the material. And this one is it's unheard of in terms of performance, and we got to introduce this. One of the customer, obviously well known, is Tesla, and it turns out that Tesla is trying to check this, but the first thing they did, they're going to sample this for SpaceX. So there's, I think, the combination of the seafoam with a conductive phenolic system, maybe top of the line in terms of technology that is available for the composite industry from a performance point of view. Okay? So before we continue, have we excited you a little bit? Is that of any interest from anyone in the audience? It's difficult to see you because of the light. Okay, it's the last presentation of the day. it's the evening. Let me continue. I hope we did. Obviously, there's some more information and some more design work to be done. Maybe a little bit of what does it mean? Just a few topics. On the left hand, you see it's a Tesco test method where you take the surface and you can measure the conductiveness. 10 to the 12 means insulating. Conductive or conductiveness starts with antistatic at 10 to the 8th, 10 to the 7th, between 10 to the 5th. We are able to get down to 10 to the 3rd, which is really electrical conductive, which is critical for shielding. But at the same time, there are applications where you want to have antistatic performance, but still an insulating material. And that's where we focus on the 10 to the 7th. So with our technology, we're dialing in the dielectrical constant on the laminate, whether it's a continuous panel, whether it's an RTM infusion, whether it's a BMC or an SMC process, and obviously also on pultrusion. We have been very successful as well to bring this technology into the glass world. So one idea was it's great to have it in the resin, but you still need to deal with an additive, a paste that is black. Cleaning is an issue, and concentration is an issue. So if we are able to get it into the resin and into the reinforcement, we thought it's going to be a perfect symbiotic effect, and that's what we did. You see, there's a university in Germany, and we have basically taken a surface veil, glass, e-glass, and performed with our SP2 additive a technology that we coat this onto the glass veil. So this means about 2 weeks ago, it was the first ever industrial-made e-glass veil or glass veil being conductive, meaning performing like a carbon veil. Obviously, it's still e-glass, so from a density, mechanical performance point of view, it's still glass, so it's not going to be compared to carbon fiber. But about 25% of all the carbon fiber, whether it's whale or mats or something, is used due to the conductiveness. Now we have an alternative, which we can combine with the resin system. So how did we do it? It went through basically through a full art. We developed a water-based system with our additive package. Then it's cured, and we have basically taken the same test that you have seen before. Even on the middle picture shows you the distance. So this is about a meter, almost up to 2 meters. And on that distance, you still get a conductiveness on the right picture of 10 to the 3rd. So, in essence, there is graphene. I think it's clear the industry, not only our industry, overall knows that graphene can deliver on the performances, on the attribute of the technology. We have taken this into the composite world and into industrial produced GRP for the first time ever. The combination with seafoam and SP2 carbon, we think is a perfect match in terms of additional performance when it comes again to lightweight, flame, and to conductiveness. We have a booth. You will see the industrial produced parts in terms of glass veil. We have samples. We have seafoam samples at Hall 5, L6. And with that, I'm going to give it over to the super excited audience with all the questions that we both will be able to answer, hopefully. Jens, help me out. Is there a question from the audience? At least one question. Okay. One second. There's a microphone that allows everybody else to also hear your question.
My question is, have you actually done EMI shielding measurements as a function of wavelengths or frequency? And how flat or changing it is?
Yes, we have. Obviously, what we do is we focus on EMI shielding performance on the laminate. I should have told this as well. We're also going to work, obviously there's some testing, and the test method is also critical to what does shielding mean. We're working with universities as well because some of those technologies are really novel. So graphene and our technology works really well between 100 hertz up to 100 gigahertz. On the very low end of the spectrum, it is still a challenge. However, there's a technology together with Seafoam where we have taken that field of wavelength that is more critical, more difficult for graphene or any 2D material to cover, and we are very confident. We have an R&D work ongoing with the university to close that gap as well. So there's a difference of 40 to 70 decibel that you can reduce, and it's obviously very important what is your spec, what is the frequency that you want to cover. When it comes to EMI shielding, the distance to the shielding is very important. So if you come and see us at the booth, we have some measurement with the laminate where we go to an electrical source, and you can see the effect of the laminate with graphene and also with Seafoam, with and without what the difference is going to take. So you can shield it down to zero with the laminate, including either a veil, the paste in the additive, or with the Seafoam technology.
The question is, what is the range of thermal conductivity of the final coating?
Okay. Everything we talked today, for us it's exciting because we have brought it to the industry in terms of industrial products, GRP, things that our customers will be using. What's really exciting is the thermal conductivity. Just to give you a number, thermal conductivity is measured in the unit of watt per Kelvin meter. Our industry, whether it's thermoset or thermoplastic, with a very high filler loading, we are happy to reach 3, 4. As a reference, metal is in the area 50, 70, depending on which metal you're going to use. With our technology, on the thermal conductivity, we can reach 15 and 20 very easy, but it's a three-dimensional technology, so the electrical conductivity is different to the thermal conductivity. But going from 3 to 15 and 20 for this industry on a relatively low filler level, carbon level, is significant. Just two more numbers. When it comes to electrical conductivity and shielding, we're talking about 1 to 2% of carbon content. And on thermal, we're talking about 5 to 15. The filler loading in a master batch or in a final compound for thermal, they're talking 50, 55% of filler. So there's a point where you don't really know, are you getting a filler that the resin is basically the glue, or you're still getting the resin that you have been chosen in the first place because of performance, whether it's polypropylene, polyamide, epoxy, phenolic, etc. So it's a significant step forward, but on the thermal, there still needs to be additional work to be done. As an example, thermal conductivity works very well in the BMC application. Bulk molding compounds, so we can take a resin with the right filler loading, up to 10, 15%, and you can replace metal that is used to cool down a composite part. And that's part of the project work we're doing for the automotive right now. Really? You have something to add?
I could probably add something to that last point. You know, with our carbon foam, we're making products that are completely vitreous, that are thermally insulating, that have a thermal conductivity of 0.3 to 0.5 watts per meter K. But then we can also dope our material with graphite. We can graphitize the vitreous carbon to some extent and reach thermal conductivities of 2, 3, up to 20. But we also make a graphite foam from mesa phase pitch. And that material can reach thermal conductivities of 140 to 180 watts per meter K, approaching that of aluminum, but yet only 1/4 of the weight of aluminum. And so, whether you want an insulating material or a thermally conductive material, and applying some of the coatings that Christian's talking about, you can really tune and engineer your composite to do what you want it to do.
So I think we have exceeded our time. For additional questions, email us, come see us. I do know that there is a GC digital show setup. I think this information will also be available online later on. And obviously happy to work on application projects, and the best of the best would be if we have a customer involved to solve their problems with composite out of our industry. Thank you for your attention.